Okay, so welcome to my talk about weak solutions of the Euler equations, which is actually very similar to the talk that Fabian gave last week. So let's start. The first part of this talk is going to be somewhat technical. I'm going to look further into the equations and the weak solutions and different questions about regularity of these solutions. It's somewhat technical. And in the end, I'm going to talk about history, where this is not technical, so everybody can enjoy that. I'm just going to talk about the history of the Euler equations. It all started with Euler, and I'm going to look into the recent developments up to 2018, which was very recently. So let's look at the introduction. I have a very nice picture here by Hokusai. This picture is also hanging somewhere on my wall. I can't see it right now, but somewhere in the house there's a picture. This picture is actually hanging on my wall. You can see a very nice wave, and I have it here because the Euler equation describes water, and it describes wave formation. So this is a very good picture. Please keep that in the back of your mind. Here we have Cédric Villani for the French-speaking of you, who describes essentially who describes in accessible terms what I'm going to describe in technical terms. What he's saying here in French is, very interestingly, the Euler equation describes water that is completely still at first, and then suddenly there's a big wave, like in this amazing picture, and then suddenly everything is very calm again. So what he's describing here in French is the very interesting fact that actually, and we will see this in detail afterwards, in technical detail, that actually it is possible that you have sort of a pond which is completely still, water is not moving, and suddenly, out of nowhere, there's a huge wave, a lot of water starts moving, and then, again, you have no water moving after like 10 seconds. So it's a very interesting effect. This is also here, but yeah, I mean, this, okay, so what he's saying here is basically this was discovered in 1990 by Schäfer-Schnirelmann and Camillo and Shekelihidi. So Camillo is my advisor for my master thesis, and Shekelihidi is somebody who he has worked with a lot. He's written his PhD thesis with him and so on. So these two, they have really pushed the theory when it comes to weak solutions of Euler equations. So this is the introduction. Let's start with what are the Euler equations from a technical term. So the Euler equations are these two equations here in the middle. We are looking for differentiable function continuously, so C1 functions v and p that satisfy these two PDEs. So the time derivative of v plus this interesting term plus the gradient of p should be equal to 0, and the divergence of v should be equal to 0. So just to note, okay, all of the notation we have nabla is I'm always only looking at derivatives with respect to the space. So I'm only looking at derivatives with respect to this first Rn here. This nabla never contains, in the whole talk, it will never contain derivatives with respect to time. Okay, very good. So these are the equations. I will talk about what they mean and why these equations are the way they are very soon. Let's look at this. So what do we have here? Yeah, that's okay. Yeah, so the physical interpretation that is interesting is v is the velocity of a particle, which is at space x and time t, and p is the pressure at that space, at that point x and time t. So let's go on very quick. So these are the equations to keep in mind. Again, I will talk about some properties of these and why they look the way they do in 2 slides, I think. But this is the important part. So okay, of course we can have an inhomogeneous version as well if we add a force F to the first equation. So here we have 0. If we replace 0 by F, you can have gravity, or you can add some interesting force to that as well. It's not super important. They have very similar properties, these two. Okay, so the interesting part is these equations, they describe the movement of fluids. So they're in hydrodynamics. They will describe essentially the movement of water. Again, v is the velocity, p is the pressure. So the equations, they will describe how does the velocity and how does the pressure of a water particle behave over time and space, right? And the first question you could ask is, like, are these solutions actually well defined for all time, right? And in fact, you can prove so that, for example, if you give some initial condition, you can prove that there will be a solution in the neighborhood of time 0, okay? And in dimension 2, it can be proven that there are solutions that exist globally. But we don't know if global solutions exist for all initial conditions in dimension 3 or above. So this is very closely linked actually to the Navier-Stokes Millennium problem, which is we are looking for existence of global solutions in 3 dimensions or higher of the Euler equations. And I mean, if you solve it for the Euler equations, you're halfway there for solving it for the Navier-Stokes equations. So this is a very tough problem, and nothing is known. Or I mean, there is something known, but the problem is not solved yet, right? Something interesting to note is that these solutions V and P, in the classical case, they are C1. So they're C1 and they're classical, then they will preserve the kinetic energy. So if you define, this is a classical physical term, if you define the kinetic energy at the time t just as 1/2 times the integral over the square of the modulus of the velocity of each particle, right? So you just take, this is the definition of kinetic energy for physicists at time t, you will see that this is constant in t, okay? So the if you have any V and P that satisfies the Euler equations, the velocity, so the energy is not going to change, right? You can actually prove this because it's a straightforward calculation that I don't remember it, but it's not super, it's pretty straightforward. You take the time derivative of E, and then you can just do a bunch of computations and you use the equations, and in the end, it turns out that the time derivative is 0, so E is going to be constant. Okay, so let's talk a bit about the Euler equations. So first of all, the physical relevance. So as I said, the Euler equations, they describe the movement of fluids, especially water. And again, they can be generalized, for example, to Navier-Stokes, where you have a viscosity term, so you can look at other fluids as well. But they have a big physical relevance because they are at the core of hydrodynamics, right? They describe the movement of water, and they're really at the core of hydrodynamics, as said. Then they are nonlinear. So let's go back. We have these equations here. So as you can see, this term in the middle is not linear. Okay, so that's the very interesting thing about these equations, is they're not linear. Maybe just as a comment, I promised I would say why these equations look like they do. So these first two terms, the sum of the first two terms here, is just the derivative of the velocity along the trajectory of a particle. So I won't do the computations, but essentially you take the derivative of the velocity along the trajectory of the particle, and you get this nonlinear term as a result. Okay, and so interestingly, these physical equations are not linear, and that makes studying them a lot harder, right? Okay, then as we talked about, they conserve kinetic energy. They are time invariant and they are scale invariant. So if you scale up or scale down time or space, they're not going to change. And what do we have? Incompressibility. So we have two equations. So the first equation here, again, we have the trajectory of the particle. You take the so this is just essentially Newton's laws so they are Newton's laws applied to the particles. Okay, is how you can think of this. And the second equation here, we have the divergence of V equals 0. This expresses the incompressibility of water. Okay, so you can prove that if you have this condition, sort of if you look at any body of water, and you look how do the particles in that body of water move a long time, if you follow all the particles, you will see that divergence of V equals 0 implies that the volume stays constant. So there's no volume loss. You cannot compress water. If you look at any body of water and how it's going to flow, the volume is always going to stay the same. So this is the second equation. Okay, very good. That is the introduction. So now, this is the classical case. So we had the classical case. It describes physical reality pretty well. So you have the classical solutions and they have physical relevance. Let's put it that way, and they have all of these nice properties like conservation of the kinetic energy. We can look at weak solutions as well. So we can look at what happens if the solutions are not necessarily differentiable. So we would like maybe to know what happens if we, if you look at all continuous functions. How could we meaningfully say that a continuous function satisfies the Euler equations, right? And so this is a very usual approach. This is very similar to what Fabian did last week. So basically, you can say if I have any function, for example, just L infinity, okay? You have a pair of functions, the velocity and the pressure, they're L infinity, they start from space times time, they go into, this Rn is the velocity, and this R is the pressure. They are just L infinity, so really a huge function space, right? We don't require them to be, C1 or something like this. They just L infinity. Then you can say that, just noting, you look at other function spaces as well. This is just an example, L infinity, but it's a huge function space. And you can say that you say they are a weak solution if they satisfy the Euler equations in the weak sense, meaning that if you take a test function that starts in space and time, and it has compact support in the, Okay, yeah. So actually, maybe I should just note here. It says L infinity from Rn times R. It should say omega here. Sorry. But anyway, so you take a function phi, a test function that is compactly supported in omega, and you look at these. You just say they are a weak solution if and only if this is satisfied for all omega. And just very quickly, how do we get to these equations? Well, if you look at, maybe I can show these on camera so you have reference. Wait a second. So we have the Euler equations here, just so you have them in mind. So you can see that this first term, the integral of the inner product of v and dt phi, I can hope you can see this. This is basically the weak interpretation of the time derivative of the velocity. And so this v tensor v times nabla phi is the weak interpretation of this nonlinear term. And p times the divergence of phi is the weak interpretations of the of nabla p, and so on. So you could, this is just the weak interpretation of all of the terms we had before, and you can see that just with this classic usual approach, we suddenly don't need any derivative of v, the velocity, or of p, the pressure, anymore, right? So if v and p are not differentiable, it doesn't matter. This is all well defined, right? Because all of the derivatives have been moved to phi. And just as a quick remark, these solutions, you can see that if you have a classical solution, v and p, that satisfies the actual Euler equations, you can see basically just by doing integration by parts that these equations are going to be satisfied. So this is also the motivation for weak solutions. Essentially, you say we just do, we look at what does the classical solution satisfy, and then we just do integration by parts, and we get this, right? And so you see that any strong solution, like any classical solution, so any solution that is differentiable and satisfies them in the sense that I said before, so you actually take the derivative and so on, it will satisfy this too, right? But additionally, now we have also, for example, L infinity functions. We can just plug in a function that is only continuous, not differentiable, for v and p, and we can still check if they satisfy this. So suddenly we have way more weak solutions. And in fact, as we will see, these weak solutions, v and p, they are not unique at all. There are many solutions. In fact, they're often infinitely many for a given initial condition, as we will see. And that's very interesting because the classical solutions, you would expect them, you would want them to be unique. And so you might ask, well, what about how can the weak solutions be not unique? Well, the answer is just that most weak solutions are not classical solutions. So there's no issue with uniqueness of classical solutions and non-uniqueness of weak solutions, because there's just many weak solutions that are not classical solutions, right? Because you have many continuous functions that solve this, but they are not differentiable, so they're not the classical solution. Very good. Okay. What do we have here? So yes. So exactly. So the question is, wait, let me check this. So yeah, so basically, okay. So I will be following essentially 3 publications by Delelis and Shekelihidi, as I said, my master thesis advisor and his friend, where they look at how regular do these solutions get. So for example, one question you could ask is, are they Hölder continuous? So one interesting question you could ask is, so the definition of Hölder continuous here is usual definition. You say that a function is Hölder continuous if and only if the supremum of the function of, let's say, xt minus the function of yt divided by x minus y to the power of theta, theta is your exponent, is less or equal than some constant, right? And so, for example, you could ask, are the solutions Hölder continuous? Or what solutions are Hölder continuous? Or what do the initial conditions have to look like so that the solutions become Hölder continuous? And are there solutions that are Hölder continuous? All of these questions you can ask, right? And how many are there, right? So these are the questions I'm going to look at. What do we have here? Okay, so we have a very interesting fact. First of all, let me just tell you a very interesting fact. If you have a solution, this is like an appetizer. If you have a solution, okay, a weak solution that is Hölder continuous, and theta is bigger than 1/3, okay? So this theta can be chosen bigger than 1/3, and this supremum stays finite. If you have any solution that is Hölder continuous with theta bigger than 1/3, then the kinetic energy is preserved, just like if it was differentiable, right? So if it's Hölder continuous with exponent bigger than 1/3, as I said, the kinetic energy is preserved. But if theta is less than 1/3, we can prove that there is always a solution that satisfies this with theta less than 1/3 that does not preserve the kinetic energy. So that's just a funny fact. I will come back to this later. This is a very interesting phenomenon, that the preservation of kinetic energy, which is a physical necessity, I mean, you would really like your solutions to preserve energy, depends on how Hölder continuous they are. okay, so here are the three publications. So they are just in the slide. So they are in my text as well, in my handout that is in the chat. So you can see here, I put the three links there. These are the three publications by Camillo and Shekelihidi. And okay, so they look at, again, as I said, they ask questions, how smooth are the solutions? How many solutions are there? And so on. So I will kind of give an overview of some of their results in the talk. Okay, that was the introduction. Very good. So now let's look at the methods that they're using. So as I said, the Euler equation is nonlinear, but usually it's easier to look at equations that are linear. So what you can do is you can transform the Euler equation actually into a system of one. So it's I mean, there are two equations, right? Two Euler equations. You can transform it into two equations that are linear and one additional assumption. Okay, so you can turn it into actually the study of a linear system with an additional assumption. So this idea is called, okay, so this additional assumption is called differential inclusion. And this principle was formulated and studied by Luc Tartare, which he's a French mathematician, and he is into PDEs. So, for example, for the Euler equations, you can see that if you have a weak solution of the original system we had, it can be reformulated as this. So if you look at the original Euler equations, you have, again, maybe let me show them just for comparison. These are the original Euler equations. You can see that this term in the middle, which is nabla times m, was previously v times nabla v, right? And you can see that suddenly, because you sort of decouple v from m, right? You add an additional assumption down below, which is m should be v tensor v minus the absolute value of v squared over n times the identity matrix. You add that assumption, and suddenly you have here a linear system, right? Because this is a linear system at v, m, and q. Because we add this additional assumption, essentially we encode, let's say, this system, again, in the linear system here, and the nonlinear relation here. And so what we can do now, this is it's a very simple trick. We just replace v times nabla v by m is essentially what we're doing, right? And using this trick, let's say, we can suddenly look at a linear system, and we can study the properties of that linear system, and then we see which solutions of that linear system satisfy this nonlinear relation. That's the strategy. Okay, so what do we have here? So so there's a general step now. So there's a general strategy. We use it's called convex integration, and this was developed by Mikhail Gromov, who is a Russian French. He was born in 1943. He won the Abel Prize in 2009, and he's now in New York. And he's a very funny guy. I think he specializes in group theory. So it's very funny that he's done something very groundbreaking in analysis when you specialize in algebra. That's very cool. So how does it work? We look at, so I'm giving the general strategy. So if you have your own PDE at home, not necessarily the Euler equation, you could try to follow that strategy and find out new things about that equation. So we're looking for functions u satisfying a nonlinear, usually a nonlinear PDE, P of uy equals 0 for all y in some domain omega, right? So again, if you come back to my example, here we're looking for the pair velocity pressure that satisfies this equation here, okay? But this can be any nonlinear PDE, right? What you do is you first turn it into a linear PDE together with a nonlinear relation. So we did that before, right? We replaced the v by m, we decoupled it into a linear system and into a differential inclusion. So that's what you always should do. Then you introduce a so-called subsolution of the linear system. So you essentially, so I'm not going to go into the technicalities, but essentially you look for a very nice solution of the linear system, right? So you look for a solution z0, so z0 should solve the linear equation, of course, and it should be as a function inside of a so-called lambda convex hull k lambda. And in our case, let me check if I have k defined. This is a bit of a problem. No, so the problem here is, okay, so I'm not going to go into this, but essentially, I'm sorry, but k is a special function space, and k lambda is the convex hull of k. So I'm sorry, because this is a bit of a issue here. I don't have k defined, but it's defined in the text, and you can find it there. So it's a bit technical, but essentially you're looking for a solution that is in a special function space that has certain properties that you can use later on. So I'm not going to go into the detail of how you construct k lambda. Again, there's a large paragraph in my handout where I go into detail about k lambda and k. And okay, yeah, so this is section 1.3 in my text. Okay, so let's say we have a subsolution Z0, we have the linear system L, and we have the subsolution Z0. What we now do is we construct a sequence of solutions. So just to recall, so in our case, we're looking for V and P, right? That's our solutions we're looking for. So we construct a sequence of solutions called ZK that approaches the boundary, in a sense, of the special function space. So again, I'm sorry that I don't go into technicalities there, but it's very hard to understand. Actually, you have a very special way of measuring how big is the distance of a solution to that function space, and it's very technical. So I'm not going to talk about it here. But again, if you look at my text, it's very detailed in there. So essentially, we look for a bunch of solutions that are in this space. So in this case, we're looking for weak solutions of the linearized Euler equation that are in the interior of some function space. Again, I apologize for not telling you exactly what kr and k lambda are, but they are special function spaces. And again, so we're looking for, essentially, we construct a sequence of solutions in a special way. And the idea is that these solutions, they converge in the sense of distributions to a locally L2, so to a pair of functions that is locally square integral Vm. And so you have the sequence of solutions that converges to two functions. So in this, also we have the zk, they converge to a z. In this case, we have we're looking for a pair velocity and the matrix, right? Because originally we're looking for a pair velocity and pressure, but we linearize the system. So now we're looking for velocity and a matrix. And essentially, our zk's, in the case of the Euler equations, are all pairs of functions vk and k, and they converge in the sense of distributions to a pair of functions Vm, right? And you can prove that if they, so again, there's a way to measure the distance to this special function space that I'm not describing here, that is described in text. You can measure the distance of the zk to that function space, and if the distance goes to 0, you can prove that this limit in the distribution sense Vm, or generally it's going to be z, at this limit is also a weak solution of the Euler equations, and that it has very nice properties. Okay, so for example, you can control the kinetic energy that this solution has. If you make special adjustments in the construction of the zk, you can essentially control the kinetic energy that your solution z in the end will have. So so this is a tool essentially which allows you to construct many weak solutions for the Euler equations and for other PDEs as well. So any PDE, you can construct weak solutions by following the 4 steps that I mentioned before. And again, I'm sorry for not going into detail. It's a bit of a structural error I made here. I'm not sorry for going into detail. I'm detail on the function space k lambda and so on. But again, it's described in the text. So if you're interested, if you want to apply this to your own PDEs at home, you can go into the text. You can see what does this function space look like? How do I measure the distance to the function space? And how do I make it go to 0? So again, I'm not going to tell you here. So the end result here is that if you have any bounded open domain in R, so you have Rn times R, then you can construct an L infinity weak solutions, right? So this is, so here this is, you say we take Vp that are in L infinity, and they solve the Euler equations. Of course, this is in the weak sense, right? Because they're not even differentiable, such that the velocity inside of that bounded domain on omega is always 1, right? And outside of the omega, it's all 0, right? So this is exactly the effect we talked about in the beginning with this amazing picture I told you to keep in mind of the wave. You can construct, with the 4 steps I mentioned before, a solution that is completely, so the water does not move at all outside of some time that is, outside of some bounded domain. And suddenly inside of the bounded domain, it's moving a lot, right? It's everywhere it's constant speed 1. So you have a wave, and then suddenly you have no more movement at all. So it's clear that the kinetic energy, for example, is not preserved, right? Because inside of that domain omega, you have huge kinetic energy, and outside of omega, you have no kinetic energy. Everything is still. So you can prove with the 4 steps mentioned before that such a solution exists, for example. So that's very interesting, right? Because again, the classical solutions, that would be impossible. Classical solutions preserve kinetic energy. It cannot be that you have no movement at all, and suddenly you have a lot of movement out of nowhere, right? There's no force, nothing. But for the weak solutions, you can actually have no movement at all, and suddenly there's a wave. So that's very interesting. And again, you can construct such solutions. Good. So that was the convex integration and the main theorem I wanted to show you. I will show you a more general theorem in a moment, but just mind you, this was the first result by Delelis and Şekilihidi, and already it's groundbreaking, right? Because this is a very absurd solution, so to speak. It's a solution you would not expect to get. You would not expect a solution of the Euler equations to have this property, especially not from a physical point of view. Okay, then let's look. Okay, so this I'm going to skip. So essentially, this is the same equation as before. I just have one additional term here, which is the initial condition, right? So if you compare with the, I'm going to put that. Let me give me a second. Where is it? So if we look at the beginning, this was what we had before. You see, this is exactly the same thing, but now we added the initial condition, right? And we can ask, if we change the initial condition, how many solutions do we get? Are there always solutions for any given initial condition, for example? Or how regular does the initial condition have to be so that we get a solution, right? So here is the general theorem that I will show you. So if you take any open set in Rn, and okay, and it has to be at least 2, and you fix a time t bigger than 0, right? So omega is now the space domain, and t will fix the time domain. And you take any function e bar that is continuous, and can I? Yeah, okay, good. So you take, why is it? Okay, so you take any function e bar that is continuous in this sense here. So it's continuous on inside of that domain, and it's with respect to space, it's integrable, right? This is what it says here. You take any function like this. So this is a huge function space here. You can take any function. Then there exists a smooth solution of the, or should it be smooth? Sorry, smooth is wrong. Sorry, this smooth is wrong. This should be weak. It's not smooth. No, wait, what? No, I'm talking, no, sorry. Very wrong. We're still in the assumptions. So you take any function like this, e bar, and you assume that there is a smooth solution of the linearized system, right? That satisfies, first of all, V0 is continuous from 0t into the space of square integral functions equipped with the weak topology, right? So W is just the weak topology. And the support, okay, of the solution is contained in omega compactly. So this means, this notation here means that the support of our solution is compactly contained in omega, right? And such that E bar of V0 xt M0 xt is less than E bar of xt for all xt inside of our domain. So we assume there's a smooth solution like this. Then we can find infinitely many solutions V and P can be determined using V. So there's infinitely many solutions Vp of this initial value problem. So there's infinitely many weak solutions that satisfy, basically, they preserve the regularity in some sense that we required on V0 and M0 and Q0. There are infinitely many weak solutions that satisfy, the most interesting thing is that they satisfy, so they're a weak solution, that's very interesting, and also they satisfy 1/2 times the absolute value of V xt squared is equal to E bar xt, right? Times the characteristic function, so outside is 0. So the point is that you have infinitely many solutions such that outside they're 0, right? Because outside this character, outside of omega they're 0, and inside they can be whatever you want, right? Because inside you can take any function E bar, and you have to make sure that this is given, right? But you can take essentially any function E bar, and that E bar will control your velocity, so the absolute value of the velocity inside of the domain. So not only can you can not only control the kinetic energy, which is already very interesting, but you can really control essentially the modulus of the velocity at every single point, right? So that's the very interesting part. And there are infinitely many solutions like this. And you can give me any function E bar, and I can give you a solution that satisfies this. So that's the very interesting part. So this is in some sense more general than the previous theorem, right? Because in the previous theorem, we just had inside the absolute value of V is always equal to 1. But now we know, well, we can also have it do whatever we want, right? Okay, so just as a quick physical interpretation, maybe, so there are a few terms in physics that are interesting. So we have the weak energy inequality, which says, sorry, this square should be outside. So we have the weak energy inequality if the kinetic energy at any point of time t is less than it was in the beginning, right? So we want the kinetic energy to just always be less than it was in the beginning, right? It can do whatever it wants, but it cannot go above the initial value. Then it satisfies the weak energy inequality. Then we have the strong energy inequality, which is when the kinetic energy is monotonically decreasing, right? So not only does it have to be less than in the beginning, but it has to be monotonically decreasing. So this is a stronger condition than the weak energy inequality, right? Because if you satisfy the strong energy inequality, you will also satisfy the weak energy inequality. And finally, we have the energy equality, which is we have preservation of kinetic energy. So we have equals here always. So all the kinetic energies are always equal. And that's, of course, much stronger than also the strong energy inequality, because if you satisfy the energy equality, you're also monotonically decreasing, and in particular, you're never more than in the beginning. You're always equal to the beginning. So the energy equality implies strong energy inequality implies weak energy inequality. And using the previous theorem, for example, this becomes a corollary. So this was a main result in the first publication by Delales and Székely-Hidi, and in fact, the previous theorem, this becomes a corollary. You can, because the kinetic energy can really be whatever you want for weak solutions. There are, for example, infinitely many solutions that satisfy the energy inequality, so they preserve the energy, kinetic energy, but there's also solutions that satisfy the strong energy inequality, but not the energy, so they don't preserve equality, they're strict, so they're monotonically decreasing, and they're not constant, right? And there's infinitely many, or I'm not sure if there is infinitely many, but there are solutions where you have the strong energy inequality and not the energy equality. And finally, you also have, for example, solutions where you have the weak energy inequality, so it's never more than in the beginning, but it's not necessarily monotonically decreasing. So this becomes more or less the corollary of the result we had before, because before, again, you can just choose any function, and you can just control the kinetic energy however you like. That's the point, right? Okay, so that was the technical part. So the technical part is over. Now comes the part that is fun for everyone, I would say, also for those who are not specializing in weak solutions of PDEs. So I'm going to talk a bit about the history. So the history, what is the history? So it started in 1755, where Euler, complete genius, he came up with these equations. He didn't even have he didn't even know what is the formal definition of a partial derivative, right? He didn't even have that, but he came up with these equations, and he formulated them that basically if you transform what he said into modern language, you will get exactly the equations as we have them today. So it's very amazing. He came up with that, 300 years ago. So here are 3 interesting publications that, if you want, you can look up. They're also mentioned in the handout, so you can look them up if you want to. Here he's talking about various things. So he starts with pressure. He starts with general equations for hydrostatics, and then he goes on. He turns that into PDEs, right? Essentially, he turns it into partial differential equations. And in the end, in the third publication, he also looks at compressible fluids. So again, all that we've done here is we have water that's not compressible. But Euler also looks at compressible fluids in his third publication. And I really recommend, actually, if you want, you can look them up. It's very informative how he did all of these, how he introduced many modern concepts, let's say, in 1755. Okay, then let's look at the history afterwards. So we have, maybe we can move this. Yeah, nice. So in 1860, this was taken up again. So we have Maxwell and Boltzmann. They started working on their theory, statistical mechanics, right? They were doing statistical theory for the kinetics of gases, and they came in touch with the Euler equations, because of course the Euler equations can also be used for gases. It's a very similar behavior, actually. And their work allowed you to basically, in practical applications with their statistical mechanics, you can now compute many constants that are needed actually in hydrodynamics just from the theory, just from statistics. You don't have to make experiments, right? And then what do we have? Max Planck and Albert Einstein, they were influenced. They read that, and they were influenced by Maxwell and Boltzmann. And the very interesting PhD thesis or dissertation by Einstein, which has only 17 pages, that's amazing. He looks at more closely at the properties of atoms and molecules with respect to the kinetic theory of gases, and he made predictions that were really so he made predictions with this dissertation that were verified, I think, a few years afterwards experimentally. So it was a very nice dissertation. I really recommend reading it, and it has to do with the kinetic theory of gases. And what else do we have? Somebody else, Kolmogorov, also a very interesting, very good mathematician. He was very big in probability theory and statistics. And so, of course, being big in probability theory and statistics, he developed his own statistical theory for hydrodynamics, and the results are more or less equivalent to the approach that Euler took with PDEs. I think it's very interesting. And that was in 1941. So that was about 80 years ago. And now to the appetizer. I talked about Euler continuous solutions in the beginning. So there was Onzaga, who he got the Nobel Prize in 1968. He asked the question, or he had this conjecture that maybe we can, I don't know if yeah, so here it is. So this is what I said in the beginning. He had this conjecture that if you take so just to note, we are on the torus now, because mathematics gets very hard if you're not on the torus for this. We're on the torus, so we are on, the circle, essentially. So the question was, what happens if the solutions, for example, are Euler continuous with exponent less than 1/3, right? So you take a weak solution, and it's Euler continuous with less than 1/3. What can we say about the kinetic energy, right? And in fact, you can prove that if theta is less than 1/3, there is a weak solution such that the kinetic energy is strictly decreasing, right? So before we had many examples, of, I said if you have certain conditions that are given, then like you give any E bar, you can have any kinetic energy you want. But here the interesting thing is you can also find solutions that are Euler continuous, but with exponent less than 1/3. And for any exponent, you can find a solution that does not preserve the kinetic energy. It's very interesting. And so this is the second part down below. And the first part is also very interesting, which is if you take any weak solution, okay, and it is Euler continuous with exponent more than 1/3, yes, then the kinetic energy is constant. Just like, and I'm sorry, I'm missing a square here. So it should be 1/2 times the integral over the absolute value squared, right? So the kinetic energy is actually constant for Euler continuous functions with exponent bigger than 1/3. So just as in the classical case, and just as a remark, right? The classical case you can essentially think of as functions that are as weak solutions that have Euler exponent 1, right? Because that's essentially equivalent. Like that's how you can think of it. So if you have Euler exponent 1, we know kinetic energy is constant. But actually, if you have any Euler exponent which is more than 1/3, then also the energy is constant. So that's very interesting. And no matter what, if you have a solution which is like, let's say, Euler continuous with the exponent 1/2, the energy is going to be constant already. So that's very interesting, and that was very hard to prove because this was proven in 1994. There was a long history for that. It took 50 years, and it was proven in 1994. I don't know what the argument was, but Terence Tao, he made a very interesting blog post on it. I think it was on his blog, he said, what's new on the Onsager conjecture or something like this, where he goes into detail in the arguments, but I understood nothing that was written there. But essentially, there's an interesting argument that I don't understand that proves that the energy is conserved if these weak solutions have Euler continuous with an exponent bigger than 1/3. And after 70 years, so 2 years ago, actually, Philip Izet, a very great mathematician, he proved that that if you have theta less than 1/3, you have solutions that are that have kinetic energy that is strictly decreasing, right? You have weak solutions that have strictly decreasing kinetic energy. That was proven 2 years ago. And in fact, so again, I didn't look into details into his arguments, but essentially he's using also the same approach with convex integration that I described. Like he essentially uses an extension of the 4 steps I described in the beginning, right? You linearize, turn it into a linear system, and you construct a sequence that has nice properties, and in the end you converge to a good solution. Essentially, he does an extension of that, and he can prove that even if they have to be Euler continuous with exponent less than 1/3, you can still find solutions that have strictly decreasing kinetic energies. And yeah, that's the end of my talk.